Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020. And the title of this lecture is Transition from Laplace Transforms to Systems of Differential Equations. Okay, so to this point we've looked at solving single differential equations. However, many real-life systems are governed by a system of differential equations. And we'll talk a little bit about the predator-prey. You could think about coyotes and rabbits, I guess. And so in a realistic setting, we'd have a differential equation that represents the rabbit population and a differential equation that represents the coyote population, but they would be dependent on the population of the prey, and the predator would be interdependent. So, to find the population of either predator or prey, we would need to solve a system of at least two differential equations. And so here is a system of differential equations down here, and this could be a predator-prey, but you see that the rate of change of x1, that's the derivative, is the prime notation, depends on x2, and the rate of change of x2 depends on x1. So this is called a coupled system. And so what we're going to do is, in this transition, we're going to use Laplace transforms to solve such a problem. And here it is. So we're supposed to solve the following system. So here is the first differential equation and an initial condition. Here's another initial condition for the second differential equation, and we want to solve this system. And notice that they are coupled because x2 appears up here and x1 appears down here. This is the end of the Laplace transform, so you're going to take Laplace transforms. Let's see how you do. Let's see how you did. Now, you see, this makes sense since the whole point of Laplace transforms was to change a calculus problem into a algebra problem and then back. So this is kind of like solving simultaneous equations. So what I'm going to do is I'm going to take the Laplace transform of the first equation, and I get this. And Laplace transform of the second equation, and I get this. And now I'm going to reorganize this and plug in my initial conditions, and I'm reorganizing so I have the capital X1s over the capital X1s and the capital X2s over the capital X2s, and I have these things. So you see, if I multiply the top equation by S all the way through and the bottom equation by -3 and add them, what would happen is I would eliminate X2, capital X2 of S, from these equations. And in fact, that's what I do over here. And so I just have, this is capital X1 of S is this, and so I solve for this. And what I'm going to do is do algebra, but it's algebra with two aspects, and the one algebra was just solving for it, but the other algebra is arranging it so I know how to take the transform. And so we do partial fractions, and this is what we get. So this is the Laplace transform of our x1 solution, and we know how to invert that very well, and this is what we get inverted. So now we have solved for x1 of t. And we can go back to the original equation, but the easiest way to do this particular example is to observe that our second equation was that x2 prime is equal to minus 6 x1 minus t, and so I can just integrate, and x2 is equal to this, and when I integrate that, I'm plugging in what x1 is and doing the integral. And so I get x2 is equal to this, and I have a constant of integration here. But my constant of integration can be solved for by using this value up here again. So I plugged that in and I found out that c in this case has to be 3 over 4, so this is x2 of t. So you see I've used Laplace transforms to solve for x1 of t and x2 of t, and we now have solved a system of first order differential equations. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.